In this video, we are going to discuss LaPlace's equation, which I have written here. So it is a second-order partial differential equation. We are going to work with the two-dimensional case, but there is an analogous three-dimensional case. And the Laplace equation is one of the most important of all the partial differential equations in applied mathematics because of how prevalent it is in real applications. The first example is the heat equation, which we had already looked at. The other example, the Laplace equation that we have here, is often referred to as the potential equation because it represents the electric potential function in dielectric medium containing no electrical charges. And it also represents the potential function of a particle in free space only acted upon by gravitational forces. So actually, hopefully, the potential function here meant something to you. It didn't mean a lot to me. But anyway, Dirichlet versus Neumann problems. So since there's no time variable here, there are no initial conditions to be satisfied, but there are boundary conditions. For the Dirichlet problem, we're going to find a solution of Laplace's equation that has given boundary values. For the Neumann problem, it's a solution of the Laplace equation where the derivative, the normal derivative, are prescribed on the boundary. So this is a boundary problem. This is a boundary problem where we set the derivative equal to a prescribed number. We will look at Dirichlet on a rectangle as our first example, and we find the solution or derive the solution. And we'll also look on Dirichlet on a circle where we use polar coordinates, and we will find a solution. From the Dirichlet problems, we're going to come up with a strategy of how to solve general problems when we have different boundaries than the one that I will show you. And then the last thing I want to say, Euler's equations are useful. I don't think they were covered per se in your book. However, there was a homework problem in Chapter 3 that talked about Euler equations, and this is what they look like. It's a second-order differential equation, but you have to be careful because this t squared here, it is not a constant. T is the variable that's involved. So we hadn't specifically talked about how to solve this equation, except that I will show you in this video how to do this. So it's kind of like bonus, I guess, if you want to think of it that way. And what we do is we make this substitution where x is equal to the natural log of t. So we transform this equation into this equation here, which we can solve, the alpha being a constant. And so we have our normal second order differential equation. So we will start with the Dirichlet problem on a rectangle, and that is we consider the problem of finding the function u of xy that satisfies Laplace's equation, which here it's u second partial derivative with respect to x plus u second partial derivative with respect to y equals 0. And we're looking on a rectangle where x goes between 0 and a, and y goes between 0 and b. And we have boundary value conditions. For this problem, this first example problem, these are the boundary values we're going to have. So other problems will have other boundaries. So here we have u of x, 0. So when y is equal to 0, and when y is equal to b, is that right? I'm sorry. Y is equal to 0, and y is equal to b, that our function u will be equal to 0. And then here we have when x is equal to 0, our function is also equal to 0. And when x is equal to a, now we're going to have our function equal to a function of y. So you want to kind of keep these straight, which things are varying and which ones are being kept constant. And we are going to be using our strategy here, and I'll remind you where we're at each point, but I'll just give you the step number we're at. But essentially, we're going to be using the strategy of separation of variables, much like we did for our heat equation, which was an example of a Laplace equation. So we're going to start by assuming u is a function of a function capital X, which relies only on the variable x, times a function capital Y, which only relies on the variable y, in which case we'll get u second partial derivative with respect to x is equal to x double prime times y, and u second partial with respect to y is equal to x y double prime. So then we can plug it in to our Dirichlet equation here, our u x x plus u y y equals 0, and what we will get is, so u x x is x double prime y, and our uyy is xy double prime, and that equals 0. we will take this equation x double prime y plus x y double prime equals 0 here, and we'll separate the variables. So all the variables with x are on the left-hand side, and all the variables with y are on the right-hand side. And here are the algebraic details, and what we end up with is x double prime over x equals negative y double prime over y, and we'll set that equal to lambda. So now we have two ordinary differential equations, and by ordinary, I mean we no longer have partial derivatives. In fact, because there's only one variable, right, you can only have normal derivatives. So our two ordinary differential equations then will be x double prime minus lambda x equals 0, and minus, y double prime plus lambda y equals 0. And here are the algebraic details I used to get the two ordinary differential equations. Now that we have the two ordinary differential equations, we should take a moment to look at the boundary conditions, and I'm just going to first remind myself that x goes between 0 and a, and y goes between 0 and b. And now if I look at this boundary condition here, this says, well, let me start, forgive me because I have x, we're going to start over here. What this says is when x equals 0, no matter what the value of y is, our function is equal to 0. So that tells us something about x. In particular, it tells us our function capital X, when the variable x is equal to 0, is equal to 0. And then we also have that the variable a, when the variable x is equal to a, then u is equal to f of y, which means my function capital X, when we plug in variable x equals a, we get a function of y, and we're going to use this later. Looking at these two initial conditions here, we have something about y equals 0 and y equals b, and they're both equal to 0. So in particular, when the function capital Y, when the variable y is equal to 0, that's this case here, we get that equal to 0. And y, when the variable y is equal to b, is equal to 0. So these are our initial conditions, and I converted them from initial conditions about u to initial conditions about the function x and the function y. The next thing I want to do is solve the two ordinary differential equations. So here I have x double prime minus lambda x equals 0. Our characteristic equation then is r squared minus lambda, and this will give us r is equal to the square root of lambda. So x is equal to a constant times e to the square root of rx plus k2 times e to the then the other value of r, which will be minus square root of lambda. And then if you recall, this form, when we have e to the lambda x plus e to the negative lambda x, that will be equal to a cosh plus sinh. And the reason why we converted this to cosh plus sinh is because it's easier to look at our boundary values. Second, we have the y double prime plus y equals 0. Our characteristic equation is r squared plus lambda is equal to 0, which means r squared is equal to minus lambda, which means r is equal to plus or minus I square root of lambda, which gives us our equation then, y is equal to c1 cosine square root of lambda y plus c2 sine of square root of lambda y. So I've written our solutions to the two ordinary differential equations, x here and y here. So what that means is our u of xy, remember u of xy is equal to x times y, so I went ahead and put x and then multiplied by y. Our next step is to use the applicable boundary conditions, and by applicable, I mean where one of the boundaries is equal to 0. So we have four boundaries, right? We have y is equal to 0 here. We have y is equal, b is another boundary. Our boundary along the x-axis is x is equal to 0 and x is equal to a. And each of those four boundaries can be equal to 0, possibly. In this case, there's only 3, and most of the time there's only 3 boundaries. Here we have y is equal to 0, y is equal to b, and x is equal to 0. Those are the 3 boundaries that are equal to 0. There is going to be generally another boundary condition that's equal to a function. In this case, it's this boundary here, when x is equal to a. And we're going to save that for later. So right now, we're doing the boundaries where one of the boundaries is equal to 0. And I'm going to start with where y is equal to 0. U of x0 is equal to 0. That was where is that boundary condition there? U of oh no, u of x0 is equal to 0. So that's the boundary I will start with. I'll plug in y equals 0 into my equation for u of xy, and here this is just x, so I'm going to keep k1 cosh, a square root of lambda x. Here I also have an x, so I'm going to keep that. Here I can plug in y equals 0, and I'll get cosine of 0 and sine of 0. And because my boundary condition says that this is equal to 0, what that means is that will work when sine of 0 is 0, so that's good. I need my c1 to be equal to 0, and then this here, no matter what the x value, will always be equal to 0. So what I get is c1 is equal to 0. So here I did y equals 0. I always like to do my variables x and y equal to 0 first. So I'm going to do x equals 0 next, and that's over here. And by my boundary condition, when x equals 0, we have u is equal to 0. So plugging in 0 for x. So here I have cosh of 0, and I have sinh of 0. Remember, c1 is equal to 0, so I can get rid of this one. But I have to plug in 0, actually not 0, because this is y. So I just leave this as sine of y. In case you need a reference, I have a graph of cosh and sinh here. So sinh is equal to 0 at x equals to 0. So this is going to become 0, so that's great. Cosh is never equal to 0, so what that tells us, if this whole expression needs to be equal to 0, I need k1 equal to 0. And now we are down to u of xy, because c1 and k1 are equal to 0, is our k2 sinh of square root of lambda x, lambda times x, and then and I just renamed this as c1 sine of lambda, square root of lambda times y. And I have to warn you, I'm really bad about this. I just kind of keep reusing the same variable names, but this c1 is not the same as this c1. It's just, I didn't want to put, I don't know, c2. I have no idea why I thought it was okay to put, I could have called this, I probably would have called, to be consistent, I would have called this k1, but for whatever reason, I just brought down k2. But anyway, when I put these constants here, I just keep reusing the same constant names, but they're not the same value as they were in this equation. And now I have one more boundary where y is equal to b over here. That's equal to 0. So I'm going to plug that in. So I'm going to get k2 sinh, and this is x, so I leave that. And I have c1 sine a square root of y, square root of lambda b. And this is equal to 0, which if we're depending on this variable here, that would mean our square root of lambda b is equal to n pi, which means square root of lambda is equal to n pi b. So this gives us a value for square root of lambda, which we plug in both here in our sinh term and our sine term. And this is a pattern you'll see in these boundaries. When the boundary is equal to 0, two of the boundaries typically will eliminate some of these terms for you. And then the other boundary will define this lambda for you. And here we are with our resulting u of xy after we applied the boundary conditions. So we only have two more short steps. The next one's pretty easy, right? The fundamental solutions and general solutions. So this fundamental solution, so for every value of n here, we have a new solution. So our u of n of xy is equal to sinh of n pi over b times x times sine of n pi b over y. So this here is a solution to our Dirichlet equation. And we have a family of solutions because there's a solution for every value of n. So our general solution is a linear combination of our fundamental solutions. So just summing from n equals 1 to infinity, I put in my coefficient. And again, this Cn, it has nothing to do with these C's over here. This is a totally different Cn. And I'm sorry, after a while, I don't know why. C for constant, K for constant. I guess I could go to M and N and S and T, but I don't. I don't go down the alphabet. I just keep reusing them as I go. Anyway, so I have Cn, sinh of n pi over b times x, and sine of n pi b times y. The last step is to use the final boundary conditions. Those are these ones here, the one we haven't used yet, that's equal to a function. In other words, u of ay is equal to a function as opposed to equal to 0. And for this, I'm going to need a little more room. Here I have my general solution, and to use the final boundary condition, that's the one where the boundary is equal to some function. That's this one here, u of ay is equal to f of y. So when x is equal to a, we have this boundary condition equal to a function as opposed to equal to 0, which these are three conditions are equal to 0. We're going to use this one equal to a function. So I'm going to calculate u of a y. So I'm going to plug in x equals a, and I get cn sinh of n pi b over a, so x equals a, and then sine of n pi b times y. This now, a and b are just numbers, so this here is a constant. So what we have is f of y is equal to a summation of some sine functions times constants, like a linear combination of a number of different frequencies of sine times a constant. That is exactly a Fourier sine series is equal to f of y. So the Cn are just the coefficients of the sine series representation of f of y. So I have our formula for the sine series for our coefficients of the sine series. And that's 2 over L, 0 to L, f of x sine of n pi L over x. So Bn, so I'm not solving for Cn right now, but just the coefficients for the sine series of f of y is going to equal to, we have L is equal to b, so Bn is equal to 2 over b integrating from 0 to b, f of y sine of n pi over b y dy. And the only difference between Bn and Cn is Cn, I have to divide by this extra constant. So Cn is equal to 1 over sinh n pi b over a, 2b integrating from 0 to b f of y sine of n pi b of y dy. Here's my final solution. Your book sometimes uses this identity to further simplify things, and we'll use this identity in an example. So I wanted to note that over here we solved the two differential equations. So we had the equation for x and the equation for y, and then we applied all the boundary conditions to our u of xy. But what we could have done is we could have applied the boundary conditions as we solved each ODE. So we could have solved this and applied the boundary condition. We could have solved this and applied boundary conditions. So I want to show you just what that looks like. It's a really quick detour because sometimes it does simplify things, and also some people, this resonates better with other people. So looking at the same problem, same two ordinary differential equations, and same solutions to the ordinary differential equation, but I will look first at the first ordinary differential equation solution and plug in the boundary condition for x. So looking over here, when I have some value plugged in for x, here x is still a variable, here I have x is set to 0 and that equals 0. So that maps to this boundary condition that the function x, when x is equal to 0, is equal to 0. And I can plug that in. Again, this is the boundary condition I'm using. When x is equal to 0, u of xy is equal to 0, or x is equal to 0. So plugging in x here, I get c1 cosh of 0 plus k2 sinh of 0. And again, if this whole expression is equal to 0, cosh is never equal to 0, which means k1 has to equal to 0. Then I can solve my second differential equation. Now I'm going to look at boundary conditions when I have y set to some term. So here I have y set to 0, so I have y of 0 is equal to 0. And I also have when y is set to b, that we have a 0. So these are my two boundary conditions. Again, when u of x0 and u of xb equals 0. So again, that's saying when the variable y is 0, then capital Y must be 0. And when the variable b is 0, the function capital Y must be 0. So I can use those two boundary conditions, plugging in for my y that I solved for. So y of 0 is equal to 0. Here I have c1 cosine of 0 plus c2 sine of 0. So if this is always equal to 0, that means my c1 has to be equal to 0, otherwise I'd have a 1. And then y of b equals 0, I have cosine. Now I take out my cosine term, and I'm left with c2 sine of square root of gamma b equals 0, which means the square root of gamma b is equal to, lambda b is equal to n pi, which means square root of lambda is equal to n pi over b. And so my final solution, u of xy, is k2 sine of n pi over bx, c2 sine of n pi over by, which is exactly what we got when we solved the two differential equations and then used all the boundary conditions. And here is an example problem to get to using this formula here for our solution, where a is equal to 3, b is equal to 2, and our f of x is given to us by y when y is between 0 and 1, and 2 minus y when y is between 1 and 2. Essentially, this is our solution here that we solved for. What we need then is to solve for c of n. So c of n is equal to 1 over sinh h n pi over b is equal to 2, times a, which is equal to 3, 2 over 2. So here, the a and b, we plugged in for a and b. We're going to integrate from 0 to b, which is 0 to 1, and also from 1 to 2, right, because the y interval is broken up. And then we have f of y sine of n pi b times y. So here, between y equals 0 and 1, we have f of y is y, sine of n pi over 2y. And over here, we have f of y, when y is between 1 and 2, is equal to 2 minus y, sine of n pi over 2y dy. We do this by integration by parts, and you can see eventually we get the answer 8 sine of n pi over 2 divided by n squared pi squared sinh of n pi 3 over 2. And here I just wrote out my u of xy, my c of n, plugged in for the c of n I found on the previous slide, and then my sinh of n pi over 2x, and my sine of n pi over 2y. Okay. And last, if you want to use this identity to simplify your expression, I have that done in this line here. So now we've done our Dirichlet problem for a rectangle. We are going to use Dirichlet for a circle. So for Dirichlet on a circle, we are going to consider the problem of solving LaPlace's equation in a circular region where the radius is less than a, subject to some boundary condition. So for the radius equal to a, and then the theta, so basically this blue boundary here, we have some f of theta. And then theta goes between 0 and 2 pi, and f of 0 is equal to f of 2 pi. So it is periodic with period 2 pi. And the first step is to transform this into polar coordinates. So we'll have u second derivative with respect to r, second partial derivative with respect to r, 1 over r times first derivative u with respect to r, 1 over r squared u second partial derivative with respect to theta. And I've rewritten it here. Again, r goes between 0 and a, and theta goes between 0 and 2 pi. And our boundary conditions, again, is that at r equals a, we have a function of theta, and then f of 0 equals f of 2 pi. Again, we have the periodicity with period equal to. We are going to follow a very similar strategy. Actually, it's the same strategy. However, because now our variables are r and theta, our Dirichlet equation is also different. So we will get different ODEs and different solutions. But we start by assuming r theta is equal to two functions, one r, which only depends on the variable r, radius, and the other theta, capital theta. This is actually a capital theta. It's like a theta with the little bars across. I know, mine look ugly. But anyway, capital theta with the variable theta, which is the angle that you're at in this circle. So our r double prime is going to be r double prime theta. Our r is just r prime theta, and our u theta double prime is going to be r theta double prime. So we plug that back into this equation here, and we get r double prime theta plus 1 over r prime theta, plus 1 over r squared, r theta double prime. The next step is separation of variables, which I actually did that work over here. I grouped all my r things over here and all my thetas over here on the right. So I get my two differential equations, r squared, r double prime plus r prime minus lambda r equals 0, and theta double prime plus lambda theta is equal to 0. And one thing to note is because our variables are r and theta, there's no time variables, so we don't have any initial conditions. We have no homogeneous boundary conditions because over here this is going to be equal to a function, so no homogeneous boundary conditions. But we do have two conditions on our solution. One, r must be bounded as r approaches 0. So when we're looking at our radius, we go up from 0 to a, but as we get really small, we want capital R to be bounded. The other thing is, again, our theta, our capital theta, our function theta, is periodic. And here I just showed the algebra I did to go from our separation of variables, where we get our r squared r double prime over r plus r times r prime over r is equal to lambda, how I get this ordinary differential equation here. And I didn't do theta for you, but I'm sure you can do it on your own. This is where we're at now. We have u, which is a product of two functions, capital R and capital theta. We did our separation of variables in order to get two ordinary differential equations, one about R and one about theta. Again, we have no initial conditions because we don't have a time variable. We have no homogeneous boundary conditions because this boundary condition out here is equal to f of a. Our boundary is, the boundary of the circle. And u of a, when r is equal to a, is equal to f of theta. So no homogeneous boundary conditions, but we do have the conditions. One, we have this condition. So r of a is equal to f of theta, and I got this from my u of a. So when radius is equal to a, so r of a is equal to f of theta, and we have that it's periodic. We do also have these other two conditions. R is bounded, so r goes from 0 to a, and when we're very close to 0, r needs to be bounded, and second theta is periodic. So the next step, 3 and 4, is to solve the ordinary differential equations and also to use the boundary conditions. So let's start with theta less than 0. So let's let theta equal to negative mu squared, where mu is greater than 0. And actually, you don't have to do this extra step if you don't want with the mu, but I don't know, I did at this point. So our first differential equation, our theta double prime plus mu squared theta equals 0. So our characteristic equation is r squared plus mu squared equals 0, which means r is equal to plus or minus mu, which means capital theta is equal to c1 e to the mu theta plus c2 e to the minus mu theta. And I just happened to choose this one. You could have solved for r first, but I solved for theta first. And I need to use the fact that theta is periodic, and I'm kind of checking off what steps I have done for theta less than 0. So I've solved for my theta. I want to use the fact that theta is periodic, which I do over here. So this can only be periodic if c1 and c2 are equal to 0, because otherwise it's not, basically this function here, e to the mu theta, is not periodic, and e to the minus mu theta is also not periodic. So this is increasing, this is decreasing, so the two added together are not periodic. So c1 is equal to c2, which is 0, which means that capital theta is equal to 0. So then when you have u, when you try to make your u of r theta, that's going to be r times r0 here, so that's u of r theta is also equal to 0 for lambda less than 0. At this point, I don't even need to solve for r because I already have u of r theta equals 0. Next, I'm going to look at lambda equals 0. So what I am going to have over here is my lambda double prime, theta double prime over theta is equal to 0, which means theta double prime is equal to 0, which means theta is equal to c1 plus c2 theta, right? If you have a function where its second derivative is equal to 0, then that means you can have something, f of x, it can have a constant, and it can also have some other constant times x. By the time you get to the second derivative, it'll all go away and become 0. So what I have then here for theta is equal to c1 plus c2 theta, but I also need theta to be periodic. So what I need is for c2 to be equal to 0. That means theta is equal to some constant. So I've solved for theta, I've solved theta, and I've used the fact that theta is periodic. So now I can solve for r. So r squared, r double prime, plus r prime minus theta, lambda r is equal to, here I have, because lambda is equal to 0, so I have r squared, r double prime plus r prime equals 0. And one thing I'm going to warn you about before you go for a characteristic equation is this r here, it's not a constant. This is the variable. So you can't just do a characteristic equation. You need to do something different. we haven't really talked about how to solve this equation because it wasn't so much covered in the book as covered by a problem in your book. But what I'm going to tell you is you're going to need to use the Euler equations, which lets you solve equations of this form, where you have your variable t squared times the second derivative of your function with respect to t times some constant alpha times your variable t times dy dt plus some constant beta times y equals 0. This is exactly this form. Your variable is r, so you have your variable squared times r double prime, that's this term, plus, in this case, alpha is equal to 1. You have your variable r times r prime plus beta, so in this case, beta is equal to negative lambda, and then you have your function r. And the way you solve this Euler equation is you're going to do a substitution. You're going to let x equals natural log of t, and that will transform this equation to d2y dx squared plus alpha minus 1 dy dx plus beta times y equals 0. So this is the substitution we are going to use, and I'll show you how that works. Also, the derivation of this formula here, I'm either going to put it at the end of this video, or maybe I'll make another video altogether to talk about how to derive this formula. I'll probably make another video. So here you go. But this is what we're going to use, and I will make a short video to talk about how this, how the derivation of this works. We'll give you an example how to use this Euler formula in this transformation. So let's say we're solving t squared y double prime plus 4t y prime plus 2y equals 0. And y is a function of t. So this t squared and this 4t here, they are not just constant functions, they are functions of t, which y is a function of t as well. So we need to use this Euler transformation. So here I can see that alpha is equal to 4, and beta here is equal to 2. So I can just plug this in. I get my second derivative plus alpha minus 1, so 4 minus 1 y prime, my first derivative, plus beta y, so plus 2y. So that gives me y double prime plus 3y prime plus 2y equals 0. And now I can plug in and find my characteristic equation, which is r squared plus 3r plus 2, and I find that r is equal to negative 2 and negative 1, so I get y is equal to c1e to the minus 2x plus c2e to the minus x. And one note, I had let x, for this, to transform it to this equation, I had to let x equal natural log of t, which is why I have x here instead of t as my variable. So you just have to remember that. I guess I probably should have written this here. I should have said let x equal natural log of t. So now my variable is x, but now I can convert it back in terms of t. I use the fact that x is equal natural log of t. So in other words, e to the x is now equal to e to the natural log of t, which is equal to t. So I substitute that in, and I get y is equal to c1 e to the x to the minus 2 plus c2 e to the x to the minus 1, which is equal to c1t to the minus 2, c2t to the minus 1. So this substitution here is the last step you're going to use to convert from y as a function of x to y as a function of t. Okay, so now back to the problem at hand. We were looking at r squared, r double prime plus r prime minus lambda r is equal to, and lambda here is equal to 0, so we have r squared, r double prime plus r prime equals 0. Using the Euler equations, looking over here, my alpha is equal to 1, and my beta, why did I say it was equal to lambda? Oh, it's equal to lambda, but lambda is equal to 0. And then x is equal to natural log of r, so we can convert it to this equation, which is r double prime, alpha minus 1, which is just 1 minus 1, times r prime, beta, my beta here is equal to 0, so I'm going to have the 0 here. So what I get is r double prime is equal to 0, and when we have the second derivative equal to 0, that means our function y is equal to a constant plus possibly a constant times x. And remember, at this point, our variable is equal to x because we made this substitution, x equals natural log of r. That's what allowed us to rewrite, transform our equation here to something we could solve. But now we need to go back and plug in x equals natural log of r so that y is equal to k1 plus k2 natural log of r. Okay, so far what we've done is we've solved for theta. We use the fact that theta is periodic. We solved for r here, k1 plus k2 natural log of r. But the last thing we need to do is check that r is bounded as r approaches 0. So as r approaches 0, and I'm looking over here, we need C2, I'm sorry, I'm really bad, I just call it whatever. It's actually K2. We need this to be equal to 0 because we don't want it to go to infinity. So what we have then for u of r theta, we have our C1 for theta, and we have for r, we also have a constant. So that means our u of r theta is just equal to a constant C1. And remember what I told you about this C1? This C1 is not the same as this C1. It's not the same as the C1 over here. I just keep using C and K's as my constants. So don't be fooled. This is just a new constant, and I just called it the same name. Maybe that's confusing, except I don't want to call my constants S, T, U, V. Eventually there are too many constants. Or the other way of saying this is our u of r theta is proportional to u of r theta equals 1. Our last case, when lambda is greater than 0, so we're going to let lambda equal to mu squared, and so you don't actually have to do this if you don't want. But then we have our r squared, r double prime plus r prime minus mu squared r equals 0. Again, here because of our r squared, we need to use the Euler equations. And our alpha is equal to 1, our beta is equal to minus mu squared, x is equal to natural log of t. You plug this in and we get r double prime plus 0, r minus lambda squared r. So now we have, and in this case, for my characteristic equation, characteristic equations usually have an r, but because r is our variable here, I use the variable s. So I have s squared minus mu squared equals 0. So s is equal to plus or minus mu, which means that r is equal to c1 e to the mu x plus c2 e to the minus mu x. And again, where did this s squared come from? This is our characteristic equation. And normally for our characteristic equation, we use the variable r. But since the variable r is already taken by this function r, I just substituted my characteristic equation variable to s. But that's okay, because we solve for s and then we can plug into here. But now I need to put this in terms of r, because we had used the substitution. Actually, I put x equals natural log of t, but actually it should have been x equals natural log of r. So I have e to the x is equal to e to the natural log of r, which is equal to r. So here we have e to the x times mu, and then c2 is e to the x times minus mu. The e to the x here is simply equal to r. So our r function is equal to c1 r to the mu plus c2 r to the minus mu. And remember, mu squared is equal to lambda. Looking at this here, I can think about plugging in my boundary condition, but I'm going to get some more information about this mu by looking at theta. So here I have theta double prime plus lambda theta equals 0, where lambda is greater than 0. I'm going to let, again, lambda equals mu squared, so my equation, my characteristic equation becomes r squared plus mu squared equals 0, so r is equal to plus or minus I mu, which means theta is equal to c1 cosine mu theta plus c2 sine mu theta. Since theta is periodic, I have this here, that will require n here is going to be a positive integer. And now I have my summary here, but one thing I did do, because this one has c1 and c2, now I rewrote r with k1 and k2, so it has different constants, because this c1 is not necessarily equal to this c1. So I renamed my constant, and now that we know that mu is equal to a positive integer, we can see that to keep r bounded as r approaches 0, k2 must be equal to 0, so r is equal to k1 r to the n. So I've summarized my findings so far. When lambda is less than 0, our u is equal to 0. When lambda is equal to 0, our u is proportional to 1. And when lambda is greater than 0, that's when we have r is equal to is proportional to Rn, and theta is equal to c1 cosine of n theta plus c2 sine of n theta. Our next step is fundamental solution and general solution. So our fundamental solution, so we look at this, we have, what do we have? U of nr, so we have our Rn from r, times our cosine of n theta. And then we also have our Rn times sine of n theta. Remember, Rn times all of this capital theta, cosine n theta plus sine of n theta, is a solution. But also because of this plus, like it's kind of a linear combination, each of them can be broken up into two solutions. So Rn cosine n theta is actually one solution. Rn sine of n theta is actually the second solution. And you can combine them and they're still a solution. And in fact, the general solution is the linear combination of all of our fundamental solutions. And you know, at one point you knew this back in chapter 2 or something, but you might have forgotten that. So when you have this plus here, it breaks down into two fundamental solutions. I'm going to use my final boundary conditions, the one where we have a boundary equal to a function. And for that, I'll need some more space. Here I have our general solution, and then we plug in r equals a into our general solution, and we get an cn cosine n theta plus kn sine of n theta is equal to f of theta. And so I went ahead and separated these two out, so I have a cosine series and a sine series. I have my formula for my coefficients of my sine and cosine series, because essentially this f of theta can be, what I have here is a cosine series, right? A bunch of cosines of different frequencies weighted by a coefficient. And then here I have a bunch of sines weighted by a coefficient. And when you sum them together, you get f. So this is exactly a Fourier series multiplied by a to the n. So what I have is a to the n c of n, my coefficient. My Fourier cosine coefficients is equal to, by my formula over here, 2 over 2 pi 0 to 2 pi f of theta cosine of n theta. This over here, this is, because we're in rectangular coordinates, it works out when we're in rectangular coordinates, but when we're in polar, this part here can just be simplified to n theta. And then my an kn for my sine series is going to be 2 over 2 pi 0 to 2 pi f of theta sine of n theta. So our final solution is going to be our general solution here with an and kn given by the formulas here from the boundary condition. Now we are going to do another Dirichlet for a circle, but with different conditions. I have the Dirichlet problem, the conditions we had just solved over here, but now we're going to change the problem a little bit. We're going to find the solution of the Laplace equation in the circle in the circular section, so it's not the full circle, but a section with the given boundary conditions. Assume u is a single valued and bounded in the sector. So here, our circular section now, r goes from 0 to a, just like before, but now theta goes from 0 to this alpha. It's no longer the full circle. And our boundary conditions are now when theta is equal to 0 and when theta is equal to alpha, that our function is equal to 0. And we have that u of a theta, so in other words, when our radius is equal to a, then we have, this is the same over here, that our function u is equal to f of theta. I should also add that theta will be periodic. So this 0 to alpha is equal to 0. It's so that we can start over and we have a periodic function. Again, we'll start with lambda is less than 0 here, and we have our differential equation, very similar to what we had before, but actually it's almost exactly the same. And then we do have a periodic function. Theta is periodic, so C1 is equal to C2 is equal to 0, so u of r theta is still equal to 0. And we have theta, so here we have theta is less than 0. Next we do theta is equal to 0, and our function is the same for theta and for r. So we have that our theta and r are both equal to constants. And then last we look at lambda is greater than 0. Again, same equation here. Our theta is going to look the same too, and we're going to use the fact that theta is periodic, but now the period is equal to alpha. So that means our mu has to equal to n pi over alpha. So we have something that looks a little bit different, and our r now is equal to k1 r to the n pi over alpha plus k2 r to the minus n pi over alpha, right? Because the mu here is the same. And since r is bounded, as r approaches 0, our k2 still equals 0, and this is our final answer for u of r theta is k2r to the minus n pi over alpha, c1 cosine of n pi alpha times theta plus c2 sine of n pi alpha times theta. And I said final answer, but I guess I didn't really mean it. We have these solutions here summarized. We have our lambda greater than 0, which we found our u of r theta. But we have a boundary condition, which is u of r 0 equals 0. So I plug that in, and I find that c1 is equal to 0. So now I have of n r theta is equal to r minus n pi over alpha c1 sine of n pi alpha theta. And then we have our fundamental solutions. So we have our r n pi over alpha times our sine of n pi alpha over theta. Remember the c1 here was equal to 0. And then we have our general solution, which sums up all our fundamental solutions. And then we use our final boundary condition, the one that we have equal to a function. And that tells us that our Cn are the coefficients of the sine representation of f theta. So this will be the final form of our answer. I have two more problems to show you. The first one is kind of long. The second one we're going to go through very quickly. So our first problem is Dirichlet for a rectangle, which is fairly straightforward. But now the difference is two of our boundaries here and here are going to equal to a function. So looking at this, the problem is find a solution of the Laplace equation. Here's our Laplace equation. In the rectangle, x goes from 0 to a, and y goes from 0 to b, same rectangle. And it satisfies the boundary condition, x equals 0 is equal to 0. X equals a is equal to a function f of y. Here we have y equals 0 is equal to a function, this should be changed, to h of x. And here we have y equals b is equal to 0. And we have the hint to consider adding the solutions of two problems. One with the homogeneous boundary conditions except for u of a, y is equal to f of y. And the other problem being the homogeneous boundary conditions except for u of x0 is equal to h of x. In other words, for part 1, we're going to solve for u of x0 is equal to u of xb is equal to 0. We're just going to solve this to be 0. U of x0y is equal to 0, but we will let this one boundary, u of ay, is equal to f of y. And then the part 2 is we set everything equal to 0 except our u of x0 boundary, which we will allow equal to h of x. So there's only, in each part of our problems, there's only one boundary that we have equal to a function. Everything else is equal to 0. Now we can do the exact same thing we did for the other problem in part 1 and do the exact same thing in part 2. Looking at part 1, again we have our separation of variables. This example, because is where I felt like it was easiest to solve the differential equation for x, which we had done. It's the same differential equation, the same separation of variables as our previous problem. So I have c1 cosh square root of lambda x plus c2 sinh square root of lambda x. And then I solved for y, which is c1 cosine square root of lambda y plus c2 sine square root of lambda y. And remember, these c2s are not equal, these c1s are not equal. So then my mu, my u then is my solution for x and my solution for y. And here I had to change my constants to k1 and k2 since they're in the same equation. And I found this easier to solve for this and then go into my boundary conditions. So I rewrote my solution, my u of xy here. And just to remind myself, I'm doing boundary conditions from part 1. And the first two that I like to do is always to choose the one where y is equal to 0 and x is equal to 0. I don't care if x is equal to 0 comes first and then y equals to 0. But here I plugged in my boundary conditions. I found that k1 is equal to 0, c1 is equal to 0. So my new u of xy is equal to c2 sinh square root of lambda x, k2 sine square root of lambda y. As you can see, I have one more boundary condition right here that equals 0. So I'm going to use that as well. U of xb equals 0. When I solve this, I see that in order for sine to give me, for sine to give me 0, I need my square root of lambda b equal to n pi. So what I get is a solution for lambda, which is equal to n pi over b squared. Oh, I'm sorry, n pi over b. So after I applied my applicable boundary conditions, this is my u of xy. C, or constant, and I just called it c, sinh of n pi b times x, sine of n pi b times y. And remember, I still do have one more boundary condition, but I'm going to use this at the very end. That's the boundary condition where u of something is equal to a function as opposed to equal to zeros. Saving this boundary condition at the very end, I'm going to go ahead and write my fundamental solution and my general solution. So my fundamental solution, for every value of n, I get a different solution. And then my general solution here is this summation of all my fundamental solutions. And now I'm going to bring in that final boundary condition that I've been saving, and I have that is equal to Cn sine of n pi b, where x is equal to a, sine of n pi b over y. And what this tells me is that my Cn, this is just a constant now, my Cn are the Fourier coefficient, or the coefficients of the sine series of f of y. And here I have my solution for part 1. I wrote down the solution for part 2, but I'm not going to do all the steps for you. But once you have these two solutions, you can add these two solutions together, and that will give you the final solution for this problem. Here I have some notes for you. The Dirichlet for a circle, we have the LaPlace's equation, and then we have the conversion to polar coordinates. I wanted to do this example because it's an example of a Neumann problem. In other words, where we have a boundary condition concerning the first partial derivative. So we're going to find the solution of LaPlace's equation inside a circle r equals a that satisfies this boundary condition here, where the boundary condition is about the derivative, the first partial derivative of u with respect to r, a theta is equal to g of theta. And this is all similar. Separation of variables, we get our two ODEs. We look at lambda is less than 0, and we find that C1, C2 is 0, and then for that reason, then our u of r theta is equal to 0 for lambda is less than 0. We go to lambda greater than 0, we get our equation for r, we find that we need to use Euler equations, and we got r is equal to C1 r to the u plus C2 r, to the minus mu. Since r is bounded, we want C2 to be equal to 0. And we summarize this here. We look at theta next, and theta we get C1 cosine mu of theta plus C2 sine mu of theta, but since theta is periodic, we know that mu must be equal to a positive integer. In other words, we're going to substitute n in here with the understanding that n is a natural number. So here we have our solution for r, here we have our solution for theta, which means we have a solution u of r theta is equal to our r times our theta. And again, n is a positive integer. So we write our fundamental solution, and actually we have two, right? Because we have our rn cosine of n theta, and actually rn sine of n theta. Because of this plus, you can, the linear combination is a solution, but also each individual component is a fundamental solution. Sometimes I get lazy and just write it all together. But then our general solution is the linear combination of all our fundamental solutions. So we have that here. The last step is to use the final boundary condition. I'll need more space to do this. Here is our solution so far. U of r theta equals C naught, that's just a constant, summation of Rn cosine of n theta plus Kn sine of n theta. And now I want to use my last boundary condition, this here. U partial derivative with respect to r evaluated at r equals a is equal to g of theta. So first I'm going to take my partial derivative of u with respect to r. So taking the partial derivative here, you can do this term by term. So essentially if I look at the, well, first of all, this over here, this here, for when we're looking at derivatives with respect to r, this whole thing is just a constant, so that gets carried down. And then my r is going to be n r to the n minus 1. Now when I plug in a, I'm going to get n a to the n minus 1, and then this constant here is equal to g of theta. So when I look at this, I'm going to separate this out into two summations. So I have my na to the n minus 1 times my cosine, and then my na to the n minus 1 times my sine, and that's equal to g of theta. So when I look at this, actually, Cn are the coefficients of the cosine expansion of g of theta, and Kn are the coefficients of the sine expansion of g of theta. In other words, what we have here, we have our g of theta, but what we have here on the left-hand side with some other constants multiplying it is a cosine series and a sine series that equals g of theta. In other words, this cosine series and sine series is exactly the Fourier series for g of theta. So here I have the formulas for the coefficients of the sine and the cosine series. So here I have my n a to the n minus 1 Cn, and Cn is my coefficient of my cosine expansion of g of theta, which is equal to, by this formula here, 2 over L, L is equal to 2 pi, that's our period, integrated from 0 to 2 pi, g of theta, then cosine. In this case, this is for rectangular coordinates, but for this, in this case, we'll just use the cosine of n theta d theta. So what that means is our Cn is 1 over n pi a to the n minus 1, 0 to 2 pi g of theta cosine of n theta. Similarly, we can solve for Kn. And finally, we have our solution. That would be our general solution here, where the constants are given by Cn and Kn. I'm sorry this video was so long, but I felt like it was important to give you a number of examples. So we looked at LaPlace's equation, which is if you have a function u, which depends on x and y, then LaPlace's equation is u second partial derivative with respect to x plus u second partial derivative with respect to y is equal to 0. We talked about the two-dimensional case. There is a three-dimensional analog, which we did not go through. And this is one of the most important of all partial differential equations in applied mathematics. There are many examples that take this form, which is what makes it so important. We talked about the Dirichlet and the Neumann problem. So first, since there are no time variables, it's just x and y, there are no initial conditions to be satisfied, right? X and y are like on the Cartesian coordinate plane. There's no time. There are boundary conditions for the function u at each point on the boundary. So in the Dirichlet problem, we have different boundary values for our u and x. The Neumann problems, we have different boundary values for the derivative of u. We looked at the formula, we looked at solving the Dirichlet problem for a rectangle with certain given boundary values. And we also derived a solution for the Dirichlet on a circle with certain boundary values. We followed this general format for our Dirichlet problems. We did something in a rectangle, and we did something very similar for a circle. It's a little bit different because now we're no longer in the xy coordinate system, but in the r theta. So our Dirichlet, our Laplace equation is different, and the form of our differential equations is different, but it's basically the same strategy. We found Euler's equation particularly useful for the Laplace in a circle because we had this form of differential equation, second order differential equation, where here this t squared is not a constant, but t is the variable that y depends on. So we needed to know how to solve this equation. What we did is we used this transformation where we let x equals natural log of t. We used this substitution, which allowed us to transform this equation into the second order equation, which we could solve. I have examples of how to use this. The derivation is in a separate video. Then we have the Fourier coefficients. I have this here for your reference because, well, you might need them if you don't remember them. And we did a bunch of problems, and that's it for this video. Thank you for watching.